Consider a system whose state is given in terms of an orthonormal set of 3 vectors. This symbol in quantum mechanics is called ket. It's normally used to represent the state of a system. So this is ket phi. So ket phi 1, ket phi 2, ket phi 3 as ket psi equal square root of 3 over 3 ket phi 1 plus 2 over 3 ket phi 2 plus square root of 2 over 3 ket phi 3. A. Verify that ket psi is normalized by calculating the probability of finding the system in any one of the states, which is ket phi 1, ket phi 2, and ket phi 3, and showing that the total probability is equal to 1. That is part A of the question. Part B of the question, consider now an ensemble of 810 identical systems, each one of them in the state ket psi. If measurements are done on all of them, how many systems will be found in each of the states? Ket phi 1, ket phi 2, and ket phi 3. To LIB Academy. In this video, we are going to be solving problems under orthogonality and orthonormality of the wave function. Solution from the Schrodinger equations. This is a general time-independent Schrodinger equation. Gives us a lot of solutions, which we use psi to represent them, and we call them wave functions. So from Born's statistical interpretation, if we have a wave function acting on its complex conjugate to get rid of the exponential sign, and we integrate from negative infinity to positive infinity, if the wave function is normalized, it should give us 100% probability of finding a particle in the system. This is just the probability density squared, probability of finding a particle in the system. And then if we integrate from negative infinity to positive infinity, it should give us 100% probability, which is 1, of finding a particle in the system. Not 0.2, which is 20%, not minus 0.3, which is minus 30% probability of finding a particle, which basically does not make sense. So from the normalization condition, psi operating on its complex conjugate, giving us 1, should indicate that this wave function is normalized. What if two solutions from the Schrodinger equation, let's say psi of n and psi of m, act on each other to give us 0? Either the complex conjugate of psi of n and the psi of m acting on each other to give us 0, then we can say the two functions are orthogonal. So combining these two ideas, the normalization and orthogonality idea, we represent it by the delta mn equal integral from negative infinity to positive infinity psi of m, the volume element, where we define delta nm should be equal to 0 for n equal m, and 1 mean n not equal to m, and 1 for m equal n. This delta mn here, nm here, is called the Kronecker delta, the Kronecker delta. So simply, if two wave functions, we find the probability density of them integrate from negative infinity to positive infinity, and we get 0, which is the orthogonality idea, then it means that the two wave function n is not equal to m, they are not identical. And if we get 1, it means m equal n, the two wave functions are kind of identical. So wave functions that satisfy this are said to be orthonormal. So that is what you need to know. Now we will start solving the question one by one. First of all, we start with part A. Part A. So now let's write the state of the system. Psi equal square root of 3 over 3 phi 1 plus 2 over 3 phi 2 plus square root of 2 over 3 phi 3. How do we verify that this state is normalized? Because that is what part A of the question is asking us to do. So we are going to verify whether this state is normalized or not. In this case, we are not asked to normalize this state. We've been asked to verify whether it is normalized. The probability of finding the probability Pi of finding a system, or finding the system in state, let's say state Qi is given by the square of the absolute value of each coefficient. So how do we interpret this? The probability of finding the system in state, let's say phi I, is equal to the square root of the coefficient here. That is what it basically means. So now let's define some terms. So we can say let C1 and P1, C2 and P2, C3 and P3 be the coefficients, be the coefficients, the coefficients and probability of finding a system coefficient and of probability of finding the system in state phi 1, phi 2 and phi 3. Once we define this whole term here, then our calculation becomes simpler. So now our examiner knows that, respectively, knows that wherever we are talking about C1 and P1, C1 is the coefficient of phi 1 and P1 is the probability of finding the system in phi 1. So we can go ahead and use our defined variables. So now for state psi 1, probability of finding the particle in state 1, in phi 1, will be equal to the absolute square of the coefficient of phi 1. Right. And the same thing happened to phi 2. It would be equal to P2, probability of finding the system in phi 2 would be equal to absolute of each coefficient squared. For phi 3, P3 equal squared. So now, what is the coefficient of phi 1? Is square root of 3 over 3. So square root of 3 over 3 absolute squared. What is the coefficient of phi 2? 2 over 3. So absolute 2 over 3 squared. What is the coefficient of phi 3? Square root of 2 over 3. Absolute squared. So the absolute sign is telling you that just square whatever is here, and the answer that you get, whether it's negative, you are going to take the positive part. You are going to take it to be positive. So doing so, this one is going to give us 3 on 9. 3 on 9. And this is going to give us 4 on 9. 4 on 9. And this is going to give us 2 on 9. Remember, for the system in state psi to be normalized, the absolute square of all the coefficients should give us 1. So all these are the probability contribution of the given phi 1, phi 2, and phi 3. So this is the probability contribution of phi 1, and this is the probability contribution of phi 2, and this is the probability contribution of phi 3. So the total probability should be equal to 1 if the wave function is normalized. So total probability, let's say PT, total probability, equal to 3 over 9, 3 over 9 plus 4 over 9, 4 over 9 plus 2 over 9, 2 over 9. And let's evaluate this and see what we get. That is equal to 1. So that is it for part 1 of the part A of the question. Once you define your variables, C1 and P2, P1, everything, you define everything, the solution becomes very simple as this. So let's see whether part A of the question is answered. That we should calculate, normalize, we should verify that psi is normalized by calculating the probability and finding the system in any one of the states and showing that the total probability is equal to 1. In this case, we've calculated the probability contribution of each of the phi, and now we add all their contribution and it gives us 1. So that is it for part A of the question. Part 2, part B of the question. Consider now an ensemble of 810 identical systems, each one of them in the state this. Remember, the state was given us in this way. So each of them are in this state psi. So if measurements are done on all of them, how many systems will be found in each of the states? So how many systems will be found in each of the states, phi 1, phi 2, phi 3? So before we start with this question, what exactly is an ensemble in quantum mechanics? Imagine you prepared 1,000 identical electrons, all in the same quantum state. In this case, all in the same of those quantum states. You measure the same property. Let's say you measure spin, you measure their spin, all of them. You measure spin on each one of them. So the full set of results from all those electrons is called an ensemble. So 1,000 electrons, you want to measure their spin, so you measure each of them. After that, the result that you get from the 1,000 electrons measuring their spin becomes your ensemble. So now we have 810 identical system, right, or ensemble, and we want to see if we perform a measurement on them, how many of these 810 will fall from each of the phi 1, phi 2, and phi 3. How many will fall from phi 3? How many will fall from phi 2? How many will fall from, will fall on, phi 1? Rather fall on them. So to do this, we need the probability contribution of each of these three set of vectors, phi 1, phi 2, and phi 3. So now, an ensemble of 810. So let's call the total number of ensemble to be 810, 810 to be n. The probability of finding the system in, let's say, state phi is going to give us probability of finding the system in state phi 1 is going to give us n times p1, which is the probability contribution of phi 1 that we calculated here to be 3 or 9. And for phi 2 is going to be n by p2. For phi 3 is going to be n by p3. So what do we get? Our n here is 810. So here is going to be 810 multiplied by the probability contribution of phi 1, which is 3 on 9 here. So 3 on 9, 810 multiplied by P2, which is 4 on 9. So 4 on 9. P3 here, which is 2 on 9. 2 on 9. So how do we get? What do we get? This will give us 270. And this will give us 360. The last one will give us 180. So this means that for our 810 identical system, when we perform measurement, 270 will fall on phi 1, 360 will fall on phi 2, and then 180 of the ensemble will fall on phi 3. So summing all these up, 270 plus 360 plus 180 will give us 810. So after the measurement, this is the number of systems that fall under phi 1, and this is the number of systems that fall under phi 2, and this on phi 3. So let's do a quick summary. The first part of the question asks us to verify whether the state is normalized and show that the total probability equal 1. And we've defined our terms. That C1 should be the coefficient of phi 1, P1 should be the probability contribution of phi 1, and the same to up to phi 3. And now we started our calculation that the probability of finding a state in phi 1 is equal to the coefficient of phi 1 squared, the absolute square. So that is what we did here to get the probability contributions of all the, phi 1, phi 2 to phi 3. And now we prove that the total probability equal 1. That is for part A of the question. And part B is asking us that an ensemble of 810 measurement were taken, that we should look for look for how many systems will fall on phi 1, phi 2, and phi 3. And then that the formula equal to the number of ensemble multiplied by probability contribution of the vectors, in which we performed our calculations to get the number of ensemble that will fall on each vector. And here state vector, they are state vectors. So that is it for this problem. Normalize the quantum state psi equal 3 times spin up times ket spin up plus 2i times ket spin down. How do we normalize this problem? This is from the idea of orthogonality and orthonormality. Or you can just say orthonormality. Let's look at the short way of solving this problem with ease. Then after that, we'll also look at another way of solving it. But let's try to solve it in standard way. So we can say let's C1 and C2 be the be the coefficients of 3 spin up and 2i spin down ket respectively. That is if you are trying to solve it in an official way. So the first thing we need to know is, looking at this state, the coefficient is 3. Looking at this, the coefficient is 2i. Our focus is on the coefficient. We are going to calculate for the norm square, and the norm is simply looking for the bra term of the ket term. So we are going to solve for this, and this is equal to the sum of the absolute square of the coefficient of each state given. So in this case, it's going to be C1 absolute C1 squared plus absolute of C2 squared. So what is C1? 3. So 3 squared plus C2 is 2i squared. Since we are looking for absolute term, we know that I is the same as square root of -1. So at the end of the day, the absolute of I is definitely going to give us 1. So we can just focus on the numerical part. So this will give us 9 and this will give us 4. So in total, 4 plus 9 gives us 13. That is 13. So now that we know our norm, just call it norm to be equal to 13. The second part is to look for our normalization constant. And our normalization constant here is equal to 1 all over square root of the norm. First step, look for the norm by summing up the absolute square of each coefficient of the state given. Then the second step, you calculate the normalization constant, and it is equal to 1 over square root over the norm. So our norm is 13. So the normalization constant equal to 1 all over square root of 13. So this now is our normalization constant. And the last step to do is to multiply the normalization constant throughout the given state. So let's do that. The state given to us was, how do you call it? Psi equal 3, which is here, spin up plus 2i ket spin down. And we've gotten our normalization constant to be 1 over square root of 13. So we are going to multiply the the normalized wave function is going to be 1 over square root of 13 multiplying 3 spin up plus 2i spin down ket. So this is our normalized wave function. We can go ahead and simplify it. So 1 over square root of 13 multiplied by 3 gives us 3 over square root of 13. Just bring whatever is here, spin up ket, plus 1 over square root of 13 multiplied by 2i you just have to focus on the coefficients. It's going to give us 2i all over square root of 13. Then bring in the remaining term. So this is a normalized wave function. A normalized quantum state. So a quick summary. First of all, you have to calculate for your norm, and the norm is equal to the absolute square of each coefficient given, right? And that is what we did here, and we've gotten it to be 13. And the second step is to calculate for your normalization constant. Normalization constant equal 1 over square root over the, square root of norm. And our norm was 13, right? So 1 over square root of 13, which is our normalization constant. And the last step to go, the last step to do is to multiply the normalization constant by the given state, which was given to you to normalize. So multiplying through gives us this. And this is our normalized wave function. Another way to solve this problem is looking for the corresponding Ket state, Bragg state. This is given us in the Ket state, the one with the greater than sign facing, the greater than sign is what we call the Ket state, right? So we are going to look at the Bragg state of it. So and what we do is that, so we are going to look at we are going to compute the product of the Bragg and the Ket. So this is the Bragg. So psi then Ket equal to, first of all, we write whatever is there, which is 3 plus 2i into bracket. And if we are done, we write whatever is here, but in this case, the operation sign is going to change. So it becomes minus. So we are going to write 3 spin up minus 2i, so I spin down that. So now let's expand it. So we have 3 slash spin up multiplying 3 slash spin up, right? So how do we write this? So 3 by 3, it should give us 9, right? So this will be equal to psi 9. So 9, we have to spin up, right? So we just open Bragg spin up slash spin up Ket, and 3 spin up multiplying minus 2i. So 3 multiplied by minus 2 gives us minus 6i, right? But what do we have? We have spin up and then spin down. So spin up slash spin down. Then we close. So now we go to this term, 2i multiplying 3. So that will give us positive 6i. So we have spin down, spin up. So Bragg spin up times spin down, close. So now 2i multiplied by minus 2i, that is going to give us 4i squared, right? And here we have spin down, spin down. So Bragg spin down times spin down. So what we do next is that we are going to assume that so spin up, spin up, spin up, spin up would be equal to spin down, which is equal to 1. And spin up, spin down is going to be equal to spin down, notice the sign, spin up, which is equal to 0. So if we have the spin facing the same direction, they will get a probability of 1. But if one is facing up and one is facing down, we get a probability of 0. So now let's go back to the problem. So we have spin up, spin down here. This will give us a probability of 0. So this term here goes 0. We have spin up, spin down here. This one will also give us a probability of 0. We have spin up here. This will give us a probability of 1. Spin down, a probability of 1. So now let's proceed. Our brass side multiplied side would be equal to. Now our major concern is on this and that. So 1 multiplied by 4, right? Let's start with 9. So we have 9, and here we have 4 plus 4. Even though we have this term here to be 4i squared, but mostly we are interested in the positive part. We know that I squared will be equal to square root of minus 1 all squared. So giving us minus 1, which will affect 4, but we are interested in positive values. So this is going to give us 9 plus 4, which is 13. 13. Then after we are done with this, we calculate for our normalization constant. And the normalization constant is just going to be the same formula. So n equal 1 over square root of bra side multiplying side get. So in this case, we had it to be 13. So equal to 1 over square root of 13. Then when you are done, you just multiply the normalization constant by the whole term. And doing so is going to give us what we already had here, this term here. So if you multiply the normalization constant by the term that was given, original term, this is what you will get. So that is another way of going by it, but I prefer the first step, the first procedure. That is it for this problem. That psi n equal x, psi m equal x squared are orthogonal to each other over the interval minus k to positive k. So the same definition, solution, if they are orthogonal to each other, then integral from negative k to positive k of psi of n and then multiplying psi of m dx should give us, it should give us 0. So now let's put in psi of n is equal to x. So we have x, psi of m is x to the power 2. So multiplying x to the power 2 dx. So we are going to evaluate this to see if the result is 0, then it means the two wave functions psi of n and psi of m are orthogonal to each other. So let's do that. So integral from negative k to positive k, x multiplied by x squared gives us x to the power 3 dx. So integrating x to the power 3, the power will increase by 1. Then we divide everything by the power. So x to the power 4 over 4. The limit of integration is minus k to positive k. So we now put in the upper limit. So wherever we see x, we replace it by k. So k to the power 4 all over 4 minus, now put in the lower limit. So wherever we see k, we'll put x, we put in minus k there. So minus k to the power 4, since the power is even, is going to give us positive k to the power 4. So all on 4. And k to the power 4 over 4 minus k to the power 4 over 4, that definitely gives us 0. So the two wave functions psi of n and psi of m are orthogonal to each other. If you found this video helpful, kindly subscribe to my channel then give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.